Okay, so we continue with our seminar. Today is the second one, and it's Zayo from National Taiwan University who will give us the seminar. So essentially it's a work we did in some modified theory of gravity, so he will schematically show us the different steps he carried on his master, and now he's continuing on his speech. So thank you, Zayo.
Shall I start?
Yeah, please.
Yeah. Hello everyone, is my voice okay to all of you?
Yeah.
Okay. So, hello everyone, my name is Chen, and I'm from National Taiwan University in Taiwan. And, this is my topic today, cosmological singularities in the Eddington-inspired-Born-Infeld theory and its possible extension. And this work is under the supervision of Dr. Marian Lopez and Professor Victor Chen from NTU and Stanford University. Next. Thank you. And this talk is based on these 4 papers, which are all published in these 2 years. And next. This is the outline. So first of all, I will give you a brief introduction of the background, including the current accelerating of the universe, the dark energy related singularities, and the singularity problems. And then I will talk about the motivation of our work. What's the purpose to study the modified theories of gravity out of the frame of general relativity? Then I will introduce the Eddington-inspired-Born-Infeld theory, or EiBI theory for short, and the significance of this modified theory. Then second part, I will talk about the first part of our work, the application of the EiBI theory to the issue of cosmological singularity avoidance. And I will show you that this theory can partially alleviate most of the cosmological singularities of interest, and it indeed turns out to be a good theory as far as the cosmological singularity issue is concerned. And then I will talk about the second part of our work, the generalization of the EiBI theory. We found that in this generalized version of the original EiBI theory, many various interesting cosmological solutions can emerge from a purely geometrical effect. For example, the primordial bouncing solutions or an inflationary state. And finally, I will give you a brief conclusion, summary in the end of this talk. Okay? So next. So let's begin. So in spite of the huge success of general relativity for more than a century, there are still some motivations for the possible extension of the theory itself. For example, if we want to consider the daytime acceleration or the singularities at high energy regimes, such as the Big Bang singularity or black hole singularity. To explain the accelerating stage, we need some kind of exotic mate called dark energy, or some kinds of modification of the theory. For example, the quintessence, generalized chapter gas, or even some higher order curvature in the action, or the phantom energy. But these kinds of modifications may cause some other problems. For example, it has been shown in the literature that the phantom energy can induce more cosmological singularities according to general relativity. Next. Okay, so this is a classification of the cosmological singularities that I will introduce in this talk. So basically, these cosmological singularities are characterized by the behavior of the scale factor and its cosmic time derivative near the singular point. For example, first one, the Big Bang and the Big Crunch, which we are very familiar with, is characterized by the divergence, the Hubble, and its cosmic time derivative at a finite cosmic time and a vanishing scale factor. And the second one is the Big Rip. It is characterized by the divergence of H and H dot at a finite time the infinite scale factor. And the following falls are rather smoother than the previous Big Bang and the Big Rip. The sudden singularity or type 2 singularity is characterized by the divergence of slot, while the Hubble rate itself remains finite at a finite big time and scale factor. The Big Freeze singularity or type 3 singularity is characterized by the divergence of H and the H top, while cosmic time factor remains. Type 4 singularity, which is the mildest one, it is only characterized by the divergence of some higher order derivative of the Hubble. The last one is the little rip. Actually, the little rip singularity is very similar to the big singularity. The big rip happens at a finite future cosmic time. However, the little rip happens in the infinite future. So actually, we may not call little rip a singularity. We may call it just a little rip. So next page. So in this page, let me use this picture to show you the behavior of the big rip singularity. So this is just the size of the universe or the scale factor as a function of the cosmic time. So you can follow the blue curve on the left-hand side. This is the beginning of our universe. That is the Big Bang singularity. And because of the radiation and the ordinary matter, the universe would move through a accelerating state. And then because of the dark energy, the universe will go to an accelerating expansion stage. However, if the dark energy is some kind of big rip, is some kind of quantum energy, is a certain equation state, for example, constant equation state, it has been shown that our universe will hit a big rip singularity in which the size of the universe and the Hubble rate grow at a finite cosmic time. Most interestingly, just before the occurrence of the big rip singularity, the bond structure in a universe, for example, the Milky Way, will be ripped apart before singularity by the huge Hubble flow. For example, the Milky Way will be destroyed, and then the solar system and the Earth finally the even nuclear. So it seems that the big rip singularity is a very dramatic doomsday for the universe. Okay? So originally, according to general relativity, we have a Big Bang and the black hole singularity. But now, because we want to introduce some kinds of exotic stuff, the phantom energy, to explain the late-time accelerating of our universe, we may have more cosmological singularity. So it seems that the singularity problems is a very important issue modern times. In classical way, there is a very useful method to tackle this issue. This is a modified piece of gravity born-infeld differential structure. And this kind of structure can be traced back to the pioneering work of Tensor and the Gibbons in 1998. And this kind of structure can even be traced back to Born-Infeld action for electrodynamics in 1934. Actually, these kinds of structures are also commonly seen from, for example, the string theory or even spatial relativity, the gamma effect. Okay. So let's back to the Tensor and Gibbons work. Most of these computational theories were considered under the pure metric formalism. So most of them suffer from ghost stability because higher order derivative in the field equation. In order to resolve this problem, recently an alternative Born-Infeld fundamental theory within Palatini formalism has been proposed. This is called Eddington-inspired-Born-Infeld or EiBI theory short. This theory was proposed by Barnatos and Pereira in 2010. So next page. So the bottom is the action of the EiBI theory. So as what I just said, this theory is constructed under the in formalism. So the metric and the connection are treated as two independent fields. Furthermore, the matter Lagrangian is also assumed to be independent of the connection field. This is a very important assumption because it ensures the validity of regional energy computation rule. And it also ensures that the matter in this theory will follow the geodesic equation defined as the physical metric G-mu. Okay? So, because the metric and the connection are independent, the connection is not the Levi-Civita connection. It is compatible with another metric, let's say the auxiliary metric Q-mu. And the relation between the auxiliary metric and the physical metric can be obtained by varying actions. And in this theory, we also assume that there is no torsion, that is, the connection is symmetric. And the kappa here is the coefficient in front of the action. It is only the parameter characterizing the theory. So in this work, we assume that a pi g is 1, so kappa is not a pi g. And the small lambda is related to the cosmological constant. This can be seen by expanding the action at the low curvature limit. You can see the pattern. If we expand the action at the low curvature limit, there are two terms. First one is the original Steinhilber action term, and the next one is an effective constant. Next. According to the Leonardo's work, they have shown that the Big Bang singularity at the radiation-dominated universe can be avoided either through a rotary effect if kappa is positive or a bounce if kappa is negative in the EiBI theory. So what is the rotary effect? I will show you in the left-hand side of this diagram. The rotary effect is the following. The universe has its minimum size at the beginning, and it stays there for a very, very long time, and it somehow starts to expand. So this is the rotary effect. And then we can further draw a picture of the dimensionless h square in terms of dimensionless energy density. You can see the right-hand side. So if kappa is negative, you can just see the third quadrant. Near the origin, it corresponds to the low curvature limit. So the universe behaves like in GR. It's a linear relation. And with the increasing of the curvature, the universe will terminate at the bounds. On the other hand, if kappa is positive, again, the low curvature limit it behaves like in GR. But if curvature in the universe will terminate smoothly at its maximum density. So this corresponds to a rotary effect. Okay? So next page. Next. So let's go to our work. So I have shown you that in the EiBI theory, the Big Bang singularity can be avoided. So it is then natural to ask whether the EiBI theory can cure other cosmological singularities of interest. So this work, we consider the first case, the theory. So we consider a universe with a radiation, matter, and a phantom dark energy component with a constant equation of state. In general relativity, this kind of phantom energy will induce a big wave singularity in the future. So what happens in the EiBI scenario? The answer is the following. So you can see the physical metric. For the physical metric, the Hubble rate is cosmic time derivative will be infinite at a finite cosmic time. So it again corresponds to a big wave singularity in the future. And in this, we also found out for the same equation of state, the singular is slightly transformed to the future in the EiBI theory compared with that in GR. Okay? And so as what I say, in the EiBI theory, we have two metrics. the physical metric G mu nu and the auxiliary metric Q mu. Both of them can define their own corresponding geodesic equation, even though we have known that in this matter will be follow this equation defined by the G mu nu. So it is also interesting from mathematical point of view to study or to investigate the behavior, the auxiliary metric, and its corresponding geodesic equation near the singular point. So that's the way that we do. How we do this? We just do a small transformation. We redefine the time scale and we define the scale factor so that the auxiliary metric can be rewritten as an FLRW form like this. Then we can further redefine auxiliary carbohydrate H2 in this way. So we found that near the degree singularity, the auxiliary Hubble rate will approach as a constant. And the auxiliary scale factor, A tilde, behaves like an exponential expansion. So it corresponds to a de Sitter stage at an infinite. This is a very interesting result because it seems that the behavior of the auxiliary metric is more regular than physical metric. So I will show you that this picture, this situation is very general in this EIBI theory. Next page. Then we turn to the sudden singularity. To generate the sudden singularity, we use a generalized Chaplin gas or PGCG with this equation of state, that is A positive and also positive. And as you can see, the universe, if the universe is filled with this kind of dark energy, then the universe will approach a minima scale vector and a minima cosmic time, along with the divergence of pressure. And in general relativity, this corresponds to a sudden singularity in the past. Next. But in the EIBI scenario, the situations are quite. The situation will be dependent on the value of. If alpha is larger than 2, the sudden singularity still exists. However, if alpha is between 0 and 2, sudden singularity will be substituted by the type 4 singularity. On the other hand, for the auxiliary metric, again we can see that the auxiliary Hubble rate HQ square approaches constant, and the scale factor seems to be contracting this. Why is it contracting? Because the cosmic time corresponds to approach minus infinity in this state. So next page. Then we turn to the big freeze case. And to generate the big freeze, we use a similar phantom generalized Chaplin gas with this equation. So in this case, if the universe approach is maximum value, both of the energy density and the pressure will blow up. And in general relativity, this corresponds to a big freeze singularity in the future. Next. However, within the EIBI scenario, we found again the situations depend on the value alpha. If alpha is smaller than -3, the universe, the big freeze singularity will be substituted by a sudden singularity. However, if alpha is between -3 and -1, big freeze singularity still exists. If alpha is equal to -3, the singularity will be substituted by a future singularity. As for the auxiliary metric, again we can see a similar result. The singularity can be substituted by a future de Sitter stage in the future. Next. As for the type 4, we use a similar phantom generalized Chapter gas with L positive and alpha bit minus 1, 0. And in GR, these kinds of phantom energy can drive a type 4 singularity in the past. Okay? And then in the EiBI theory, well, it seems that this page is completed. Please go to next page.
So I made a mistake. In which slide can you read what is at the top?
Now it's 19.
So type 4 and then the next one, no?
Yeah.
Okay. Type 4 in EiBI.
The page with a clearer form.
Okay. With a lot of forms.
Yeah. So because previous pages contain too much detailed conclusion, too much detailed results, so here I will just brief summarize the result for the type 4 singularity in the EiBI set area. So actually, what we derived is that the type 4 singularity may sometimes be cured, or sometimes exist, and even sometimes worse. So seems that we didn't say anything. So next page. So last case is the little reef case. The simplest dark energy equation of state driving the little reef in GR is this. It's and the square root of the energy density. And in the EiBI scenario, we found that the physical metric also corresponds to a little reef in the future. However, for the auxiliary metric, it again corresponds to a distant stage in the future. Okay, so next. So this page is the big table, a brief summary. You can see the physical, as for the physical metric, except for the big reef and the little reef, you can see that the EiBI theory can partially alleviate most of the multiple singularities of interest. And even for the auxiliary metric, the behaviors of the metric is rather and is even more regular. This next. So again, as what I say, in the EiBI phantom model, the most singularities in GR are alleviated in EiBI phantom model. And the behavior of the auxiliary metric Q is more regular than that of the metric G. And in this work, we also use the cosmographic approach to constrain this model. And we found that the cosmographic parameters will pick up the parameter space in which the occurrence of S type 4 singularity or the S lottery effect is preferred. However, as for the future doomsday, we have to say that the higher order cosmography parameters are needed because the error of the parameters so far is still too large for us to give a accurate enough forecast of the future state of the universe. Okay, so next page. So let's turn to our second work. So in our second work, we just add a pure trace term to the original EiBI theory. We added pure trace term to the determinant in the action. So you can see the mu times R. This is coefficient beta. And this kind of multiplication corresponds to the most general rectangular tensor that contribute to the first order of the curvature. So originally we have only cup times R mu in the action, but it is not the general form. If we want to consider the most general form, we need to add a pure term like this. So, and this kind of action was considered but not yet in the Palatini formalism. Okay? And it is also expected that this kind of amendment can provide more degrees of freedom to construct cosmological solutions. And then if we expand the action at a log curvature limit, we can just see the red colors two terms. The first is again the angular action term, and then the second term is the effective cosmological constant. So if we want to ensure that theory will cover original relativity, low curvature limit, we have this area. Alpha or beta should be 1. So actually, in this theory, we have only one more degree of freedom than original EiBI theory. But even though we have only one more degree of freedom, the field equations in this case still very complicated. So in this, we will use the parametric Riemann equation to show logical solution graphically. To be more precisely, we define rounding variable x and express the half square and the energy density rho as the functions of x. Then we can apply the relation h squared and the energy density by varying the rounding value for x. Okay, so the result is the following. Okay, so in this work we will first consider a Chen dominated universe. So U is equal to 1/3. You should note that if beta is equal to 0, then alpha is equal to 1. Then this theory will recover exactly original EiBI theory. What we are interested in is the deviation between this theory and the original EiBI theory. So allow the value of beta to be different from this. So first of all, we consider beta between 0 and 1/4. The result is the following. Alpha is negative, you can see the third quadrant. The universe will start a Big Bang polarity at a high curvature regime. However, if kappa is positive, you can see the first quadrant. If beta is very close to 0, the universe, there is something solution at a high curvature regime. Then, with the value of beta increase, the H line here equals to a southern singularity path. Then, because the universe will start from the big singularity, as you can see, line, and then beta is equal to a big bang singularity path. So here I want to stress one more thing. You please to page 10. Okay. So page 10. In the original EiBI theory, the bouncing solutions only appear in the alpha negative region, and it has been shown in the literature that these bouncing solutions are not stable because of the imaginary of the sound speed. So we can regard this as the price we pay to generate the bouncing solution in this EiBI theory. So actually, general relativity, the bouncing solution may correspond to a violation of the energy condition. But in this case, we do not have to say any energy condition and we can generate a solution. But price is the solution is not stable. Let's go back to our page 20. In our case,
next page,
25. Okay.
Yeah. So radiation and bits are larger than 1/4.
Yes, between 0 and 1/4.
Okay.
Thank you. So in this case, we have a bouncing solution at a different parameter space. This bouncing solution happens if kappa is positive. So it is also interesting to investigate whether this bouncing solution is stable or not. But this, if we put it as the actual works, I put the question mark here. And furthermore, as you can see, we have a big bang in 1/4. This is a new beta equal to 1/4. This generalized EiBI theory we cover and in this theory, radiation-dominated universe will indeed start from Big Bang. So next page. Now, beta is larger than 1/4. Again, see the alpha is negative. See the third is the function in alpha if alpha is positive, is the universe from the singularity attack. Okay, so next. Specifically, if beta is just smaller than 1, there is threshold the H function. Alpha is so this after the Big Bang and the follow up enter is GR.
Sorry, Xavier, can you repeat because there was a slight problem with the connection?
Okay.
The last just
So in this case, if beta is just slightly smaller than 1, there's a O in the H square function. You can see, for example, the dashed line in the figure. And this kind of behavior corresponds to a decision stage after the Big Bang singularity and followed by the standard expansion of GR. So in this case, the universe will start from the Big Bang singularity from the very right-hand side of the figure, and it falls down along the curve. It enters the inflationary stage, the very region, then it moves the standard expansion of GR. So this solution is very interesting because we don't need any other field or the scalar field or something else to drive these logical solutions. We only have a radiation-dominated universe, and this kind of solutions emerge only from a purely geometrical effect. So this kind it also forces more further investigation. So next. Is solution. So in this talk, I have talked about the EiBI theory and its application to the cosmological singularities issue, and I show you that most of cosmological singularities can be partially alleviated within the EiBI theory, even though the avoidance not completely general. For example, the big rib and the little rib are still this. We can do this kind of singularity. But with the cosmology approach to Chen, and we hope that the cosmography parameters data pick up the space, the I4 singularity as local effect is. This seems to be a good news for the EiBI, even though the avoidance of singularity is not general. And in our second work, we add a pure trace term into the determinant, and we found that after this amendment, various cosmological solutions merge, including inflationary or even primordial solutions. And these cosmological solutions very natural because we don't need any other exotic stuff to drive these solutions. We only have determinant. These solutions are very natural and worth more investigation. Okay? So that's all.
Thank you, Xavier. Well, maybe it has been very short to be a seminar. Maybe you needed maybe 10, 15 minutes more, but as you are PhD students on your first year, so that's not too much. Maybe the next time you could extend it a bit more. So, for example, you didn't speak much about cosmography, and you can have it come back. But thank you very much. It has been very nice. Question, comments?
My question is there any way EBL theory is related to a scalar tensor theory with non-minimal derivative couplings? Because
You mean this, whether this theory is related to some kind of scalar tensor theory or not?
scalar tensor theory with non-minimal derivative couplings, because it is similar where you replace G mu nu plus R mu nu or with the Einstein tensor. It is similar. Construction is similar.
So what he's
Yes,
asking is, can we do some probably some conformal transformation, something like that we provide this as scalar tensor here? That's what you're asking.
Yes, I think so. This is because it is also the case in the Palatini bar theory. So maybe we can do this after some conformal transformation. Yeah.
Another question is in the conclusion. I mean, you mentioned inflationary state emerge in radiation dominated universe. Is it standard
Yes.
inflation?
No, this we don't know.
It's not standard inflation.
No, what he meant is that.
Oh, it's not standard inflation.
What he meant
It is just the knowledge of the stage in which the h square is almost a constant. So we may call it an inflationary like state.
What he meant is that if you have a radiation fluid or this kind of theory, you will get some geometrical solutions which are almost the same. But we didn't work out yet the perturbation. So if you're asking what is the PS or NS, this we don't know. So this is something.
Yes, it deserves more investigation.
One last question. In one of your slides, I think it is EB theory with a trace term, where you show in one of the cases it reduces to R plus R square.
Sorry,
Is it
I cannot.
in one of your slides you write? Yes.
So you mean when you expand the action of the last word,
Yes.
then you have alpha plus 4 beta, R plus blah.
Yes.
So
You mean page 24?
I do not, it's modified EBI with a pure trace term. You have the
Yes.
action and then the
No curvature limit?
yeah, in low curvature limit, it reduces to R plus R square.
Yes, well, I have an R square. Yes.
Yeah, I'm just thinking of Stravinsky inflation.
But this is different. In the original Stravinsky inflation is constructed under the metric formalism. But in this case, this is just the Palatini formalism. And in the Palatini formalism, R plus R square will not induce the inflationary state.
Okay.
They are different. Yeah.
Thank you.
You're welcome.
Any further question? Comments? Okay. So I have one. I already mentioned to you that in vacuum, as we know, this type of solution that Simon was asking is not GR. With many particular that vacuum solution will be different. I know it's a very difficult calculation because this is very messy. Maybe at some point we should come back to this. Because probably Schwarzschild and things like that would be different.
Yes,
Different
of
than
course.
EBI. This is just a comment.
Okay.
I think there are no further comments. Thank you very much. 谢谢这里. So, just one. And one an, also an. I never remember. One an?
It's 8 o'clock, so it's 1 hand.